Welcome to this presentation of LINSTOR at FOSDEM21. My name is Altnoeder and I've been working for Linbit as a software developer since 2013. So what is LINSTOR? LINSTOR is a storage automation system built on top of already existing storage technologies that are available on Linux. That includes LVM, CFS and DRBD. In contrast to many other storage systems, such as Ceph for example, it provides block storage, as opposed to, for example, object stores or databases. There is a strong focus on replicated volumes in LINSTOR, and to replicate volumes, LINSTOR uses DRBD, which is also developed by Linbit. And I'll tell a bit more about DRBD later in this presentation. Normally a LINSTOR cluster consists of at least 3 nodes, and a typical LINSTOR cluster will have about 3 to 30 nodes. There are some clusters around with more than 400 nodes, so it is quite scalable. The nodes where new volumes are placed are selected automatically by LINSTOR, depending on configurable settings and constraints. LINSTOR is typically used as a storage provider for various platforms. There are a number of connectors available for integrating LINSTOR into those platforms. And you can see the most important ones listed on the slide. Connectors are separate modules and are run outside of the LINSTOR server. One LINSTOR cluster can be used to provide storage to multiple platforms. Not necessarily multiple instances of one platform, because some of those platforms might run into collisions with naming, for example. That depends on the platform. Let's take a look at how LINSTOR can be integrated in some different scenarios. The first one is a typical hyper-converged infrastructure, where you have local storage in the nodes that actually run your workloads. Whenever a workload migrates to a node that has no local replica of the workload's data, it causes network traffic for accessing remote storage. So performance-wise, it will make sense to move the data to the node where the workload is actually running. LINSTOR can achieve that by increasing redundancy temporarily. So it'll just create a new volume on the node where the workload has been moved to, and it'll resynchronize from other storage nodes. While it is resynchronizing, the existing replicas are still usable, and even the new replica is already usable during resynchronization. Once resynchronization is complete, redundancy can be reduced again. So you're basically just dropping one of the existing replicas from one of the other nodes. If you have a setup with separate storage nodes, then LINSTOR can use DRBD to provide access to remote storage. That's what we call a DRBD client, and you'll hear a bit more about that a bit later in this presentation. It works just like a normal DRBD volume, but it does not have any local backing storage. So you can think of it as working similar to iSCSI. Whenever a workload moves to another node, LINSTOR creates a DRBD client on the node where the workload is being moved to. If a storage node fails, that failure is transparent to the hypervisor or container or whatever application you're running. The DRBD client simply accesses one of the storage nodes that are still online. Let's take a look at LINSTOR's architecture. The LINSTOR server consists of 2 components, the controller and the satellite. Those are 2 independent modules, and you can run both on the same node. If you run the controller and satellite On the same node then, that's what we refer to as a combined node. Every LINSTOR cluster needs at least one controller, and optionally you can have multiple backup controllers. Satellites run on all nodes that provide storage. For communication between the controller and the satellites, LINSTOR uses TCP/IP connections, and those can be SSL TLS encrypted. You'll normally do that except in test scenarios where you can use unencrypted connections as well. There's a command line interface available, and you'll use that especially during initial configuration. Connectors integrate LINSTOR into various platforms, so you normally don't see LINSTOR. Instead, you'll just click New VM, specify the size of its volume, and then hit OK, and predefined profiles in LINSTOR will create a volume with certain settings and a certain number of replicas. The entire configuration is stored on the LINSTOR controller. The satellites are stateless and receive the configuration from the controller. For persistence, the controller uses either SQL databases or etcd. By default, it will use an integrated H2 database. That means you don't have to start it manually, or just start with the controller and also stop with the controller. We have also used the controller with PostgreSQL, MariaDB, and DB2 for controller persistence. The best choice is PostgreSQL, since it's an open source database and available for free, and also because it was originally used when development of LINSTOR started. etcd can be used as an alternative, so instead of a database, but it has certain limitations. Because it is not really a database, it's just a key value store and can only store strings. Let's take a look at what LINSTOR uses internally to provide storage. One of those components is LVM, which is Logical Volume Manager. It's one of the components that LINSTOR can use to create backend storage on a single node. LVM was originally invented on AIX, IBM's Unix-like operating system. The Linux implementation of LVM is very different from the one in AIX, so it has different commands with different parameters. But the principle is the same. You have a bunch of physical volumes, that would be hard disks, SSDs, NVMEs, or even RAID volumes. And then you can combine those to create a volume group. From the volume group, you can create an arbitrary number of logical volumes, and each of those can be smaller or larger than any of the physical volumes in your volume group. Logical Volume Manager also supports thin provisioning. A thin pool is simply another logical volume used as a backing store for thinly provisioned logical volumes. Thin provisioning uses a copy and write mechanism, so it can maintain multiple snapshots efficiently. You need to be careful with thin provisioning though. There are some drawbacks, especially if you over-provision. That means if you create volumes that are larger than the actual physical size of your volume group. Free space is essentially a fantasy number in thin provisioning, so it's quite easy to lose track of how much space you're using and run out of space unexpectedly, and that can cause I/O to freeze, and then you'll have a downtime. Instead of LVM, LINSTOR can also use CFS or NVMe over fabrics. CFS support in LINSTOR has similar capabilities to LINSTOR's LVM support. LINSTOR uses DRBD for replicating volumes. DRBD is a Linux kernel module that provides replication of block devices, and it is also developed by Linbit. It's a free open source software under the GPL. DRBD version 8 is upstreamed in the Linux kernel, and DRBD version 9 is not yet upstreamed, but upstreaming DRBD version 9 is planned in the future. LINSTOR requires DBD version 9. It does not work with DBD 8. DBD 8 could only provide 2-node clusters, so that would not make too much sense with DBD 9. With DBD you can run synchronous or asynchronous replication. Asynchronous replication mostly makes sense for long-distance replication and for disaster recovery. DBD can simply replicate any block device as long as it's writable, and it doesn't really care about the contents of whatever block device you are replicating. So there could be a file system on it, and it doesn't matter what file system it is, or it could just be raw data, for example from a database. The replication link used by DBD is a TCP/IP link, just like the LINSTOR links. DBD does provide authentication, but it does not provide encryption. So if you run it through the internet, you should probably run it through a VPN or IPsec link. Multipathing is also provided by DBD, but only for failover capability. It does not provide load balancing, or at least not without additional add-ons. DBD normally uses one primary and one or multiple secondaries. Those are different roles in DBD. There is a dual primary mode, but it requires a much more complex setup and has certain limitations. That is mostly used for live migration of VMs. It does not make much sense for anything else in combination with LINSTOR. A resource provides access to the storage volume by applications if it is in the primary role. The secondary only replicates everything that is written on the primary. DBD also supports multiple volumes per resource as opposed to multiple resources, which it also supports. And there are some important differences here. If you have multiple resources, each of those resources has its own replication link. And each of those resources can be made primary on another node. So that's how you can build active-active clusters, for example. Each of those resources can also be started and stopped independently. And the replication link of each resource can be connected and disconnected independently. It's different with multiple volumes in one resource. In that case, you only have one replication link for all the volumes in that resource. And also primary and secondary is selected per resource, not per volume. So either all of the volumes are primary on a specific node, or all of the volumes are secondary. You cannot have one volume primary on one node and another volume primary on another node. With multiple volumes in a resource, either all of those volumes replicate or none do. And that makes sense whenever you have related data spread out over multiple volumes. An example would be if you have the actual data of a database and database logs of an SQL database spread out to multiple volumes. That's also why we call it a consistency group. You can have up to 32 replicas per resource. You can have more than 32 nodes in a LINSTOR cluster, but at any point in time, the resource, so a single resource, will only be available on at most 32 nodes of that cluster. Other resources can be made available on different subsets of nodes of the same cluster. Any typical setup will have 3 to 6 replicas. So in practice, the theoretical limit of 32 is mostly useful because it allows you to move resources around and to add diskless clients that access storage remotely. You do not normally keep more than 3 to 6 actual copies of the data. A DBD client is an intentionally diskless resource that allows access to the data that is stored on other storage nodes. If a disk of the actual storage nodes fails, DBD does basically the same thing. It just goes into diskless mode and works the same way a client would. It continues to work, and read and write access is still possible on that node. Once you replace a failed disk, it will resynchronize from the other storage nodes. One of the more recent features of DoD is quorum logic. The idea behind quorum is that if the network splits the cluster into multiple partitions, obviously only one partition can have more than 50% of the nodes. And that'll be the only partition that will still allow changing the data on the volume. And the other partitions will either freeze I/O or they will give you an I/O error. And that is configurable. You can set some additional constraints in DoD. For example, a minimum number of nodes, you can increase that and require, for example, 70% of the nodes to be online. Obviously, you can't do less or equal to 50% because then quorum wouldn't make any sense. And minimum redundancy is where you can specify a number of disks that must be online to achieve quorum majority. So a certain number of disks need to be actually writable, even if a number of nodes are online for quorum majority to be achieved. For increased performance, you can use InfiniBand or Dolphin Express cards with DoD. And there's also a commercial add-on that provides RDMA, which is Remote Direct Memory Access. That reduces latency. That is not included in the open source version of DoD since it is a commercial add-on. There's another add-on that allows you to keep metadata on PMEM or non-volatile memory DIMMs. And metadata is necessary for DoD to keep track of synchronization state of each DoD volume. Apart from using LINSTOR directly on the nodes that run your workload, it is also possible to build dedicated storage clusters and then connect other nodes using iSCSI or NFS. There's a project called LINSTOR Gateway that integrates LINSTOR with HA cluster software. In that case, storage is provided by LINSTOR, and high availability for iSCSI and NFS resources is provided by Pacemaker and CoreSync. Pacemaker is a cluster resource manager, and CoreSync is the communication layer for that cluster resource manager. Pacemaker is pretty much the standard cluster software on Linux. What LINSTOR Gateway does is it integrates LINSTOR with Pacemaker so that if you create a new resource, all the configuration will be done automatically in LINSTOR and in Pacemaker. I have a 4-node LINSTOR cluster here, and this is just a test cluster, just virtual machines. You can see the LINSTOR processes running here. So those are 2 Java virtual machines. LINSTOR is written in Java. It requires Java version 8 at least. Obviously newer versions will work. And it's running 1 controller and 1 satellite on this node. And let's go over to this node here, and this is not part of the LINSTOR cluster. It's not running any controller or satellite processes, but I will use it to run the LINSTOR client. And you could just type commands directly here in the shell, but I will just type LINSTOR and enter interactive mode because that's more convenient. And let's take a look at the node list, and you can see that we have those 4 nodes. One of them is Romulus, this one over here, that runs in combined mode, so there's a controller and a satellite on this node. And the others are just satellites. All of them are running the LINSTOR processes. All of them are online, so the controller has contacted those satellites and is talking to them. And in this test cluster, it's not an encrypted connection, so it doesn't say SSL TLS here, it's just plain text. The LINSTOR client can run anywhere, does not need to run on any of the nodes that are part of the cluster, and it just uses another TCP/IP connection that can be encrypted, but in this case it's just plain text. So the next interesting thing is the storage pool list, because this is what LINSTOR uses for creating any of the resources that I create automatically with LINSTOR. And the first one, default disk list store pool, that one is always present. You don't have to create it, that is created by default. And it's diskless, it's used for DBD clients that do not use local storage. The other ones, fat and thin, those are just names, so I use one for an LVM fat provisioning pool and the other one for an LVM thin provisioning pool. And you can choose whatever name you want. I just like obvious names, so that's what I use. The volume group here is DBD pool, and as you can see, the thin provisioning pool is placed inside the same volume group that is also used by fat provisioning. So the thin pool takes some of the space of the fat provisioning pool. And that works with LINSTOR, so that doesn't cause any problems. The thin pool is a logical volume inside of the DBD pool volume group, if you're wondering. Then what we also have is a list of network interfaces. I'll show you the ones of the controller node here. And those network interface definitions are used first for controller satellite communication in LINSTOR. So it says satellite connection here, and you could use any of those. You can also use any of those network interfaces for DBD replication. So I could specify one of those network interfaces to be used for the replication link of DBD. Let's take a look at the resource definition list. This should be empty, and it is. And that means we can create our first resource here. So we'll start with the resource definition, and I have to specify a layer list. I want to use replicated volumes, so I need to use DBD, and I need to have some storage, local storage, where DBD can write to. So that's what I'll use, a layer list of DBD and storage. You could have additional layers in between here, so you could have DBD on deduplication, on encryption, on storage, and that's what you specify with the layer list. Then the last thing we need is a name for our new resource, and that'll be FOSDEM21. And we also need a volume definition, because a resource is only a container for a number of volumes, in this case only one volume. And now we should find this in the resource definition list and also in the volume definition list. And you can also see that LINSTOR assigns some resources automatically. So for example, a TCP/IP port to be used by DBD replication links is specified here, and that's selected automatically from a pre-configured pool of TCP/IP ports, a TCP/IP port range. And it works kind of the same way for minor numbers for DBD's block devices. So that is also automatically configured from a range of minor numbers from a number pool. And that didn't do anything yet, so those are just definitions that are going to be used whenever I actually create a resource from those definitions. And we're going to do this now. So resource create, we want to create from the FOSDEM21 resource definition, and we want to have everything go into the fat storage pool. And I will let LINSTOR auto place on 3 of my 4 nodes automatically. So it will automatically select 3 of my 4 nodes. Here we go. And resource list. So you can see those are the same. It uses whatever the definition says. And also let's look at the volume list. And we have def DBD 1000 with about 100 megabytes. It's not in use anywhere. So what we can do now is, since it was placed on this node that I have open here, we can just create a file system on this volume. Let's do this. And let's mount. And let's even create a file here. So everything is set up. The volume works. I can use it immediately. And let's check whether replication actually works. And let's go to one of those other nodes that also has the resource. For example, let's go to Kronos. And let's mount here. And here's our file. So that's all you need to do in LINSTOR to get a replicated volume on multiple nodes. You just create the resource and you can immediately write to one of the nodes, and all the other nodes will just replicate all the data that it just wrote to that volume. It's pretty straightforward. Now let's add another replica, and I will clean up here first. I can just take a look at the resource list, and as you can see we have the resource on Kronos, Remus and Romulus, and there is another node that is called Vulcan, and I will create another replica of this same resource on that node. And same storage pool, just goes into the fat pool, and that will also automatically resync all the data that I already have on the other node. So if I go to Vulcan and I mount here, then again I have all the data that the other three nodes originally had, because it resyncs automatically. And then finally I can go back to triple redundancy by removing the existing replica, for example from Kronos, and by doing that it's really easy to move data around in a LINSTOR cluster. So you can just create additional replicas, you can increase redundancy, you can increase it permanently, you can increase it temporarily, you can remove replicas and reduce redundancy at any point in time. It's really easy just using those resource commands in LINSTOR. Let's clean up again and I'll show you how to resize volumes. Let's take a look at the size of the, where is it, DevDBD1000. Let's take a look at the size of that block device, and it's about 100 megabytes, as we can see in the volume list. And some of the space is used for DBD metadata, so it's usually a bit larger than what you specify because of rounding that takes place in LVM. Let's even mount this volume while we are resizing it, makes it a little bit more interesting. And now obviously we would have to resize the backend storage on each node that replicates, so that all nodes have enough storage to keep the larger file system. And then we would have to resize the DBD on top of it, and then the file system on top of DBD. But regarding everything that happens beneath DBD and DBD itself, everything is taken care of by LINSTOR. So all you have to do is volume definition, set size, and then you go resource name, volume number, volume 0, and the new size. And you can normally only increase the size, because obviously if you reduce the size that would damage your file system. So as long as that is online and actually has volumes, it will not allow you to reduce the size. And it told us that everything was successful, no error messages, so it should be available now. Let's check the block device first, and it has increased to about 130 megabytes with some rounding. But let's look at the file system, and that has not changed yet because LINSTOR does not resize the file system, so we have to do that manually, and it depends on the kind of file system that you have on this device, whether you can do that online or not. With ext4 you can, so that's what I'm doing here. And now you can see it has increased from a former 97 megabytes effective to a 116 megabytes effective size. So there's some overhead in the file system. It's not actually 120 megabytes, it's about 116 that you have free now. The next thing that I would like to show you are resource groups, and let's clean up again here. Let's start over with resource groups. So often you would not want to create each resource definition, volume definition manually and then set the same properties on all of them manually. It would be much more convenient to have a profile where you can specify properties that will automatically be set on all the resources that you create. And this is also how using LINSTOR with Kubernetes and OpenStack, OpenEBL, and all those platforms work. You just create a profile that tells LINSTOR what to do whenever it gets a resource request for that profile. And then all you have to do in those other platforms that LINSTOR integrates with is select that profile. I'll just create a new profile, and those profiles are called resource group. And I'll call it triple because I'm using triple redundancy here. But again, that's just a name. You can name it whatever you want. I just like obvious names. And what I'm going to configure here is that all the resources that are created from this resource group are going into the thin storage pool. They are all going on 3 of my 4 nodes. And again, a layer list of DABD and storage. So I want it replicated with DABD directly on top of LVM. And that's my new resource group. Let's list the resource groups. And there is already one here that is called default resource group. That one is created automatically if you create resources manually without any resource group. LINSTOR will just create it automatically for you so that you can set properties for all those manually created resources that will be inherited by them. And our new one is here, triple with a place count of 3, storage pool thin, and the layer stack of DBD on top of storage. And we also need to specify that it has one volume for each resource created from the triple resource group. And I'll show you the help for this command real quick, because otherwise the command doesn't seem to make a whole lot of sense without knowing that you could specify the volume number that is used every time a resource is created for the triple resource group. And if you don't, then LINSTOR will just use the lowest one. So if I just do volume group create triple, that will just tell the resource group that every resource that is created from this profile, from the resource group triple, is going to have one volume with volume number 0. It doesn't say anything about the size or type of the volume or anything like that. It's just the volume number, it's just the definition again. And then you can use this profile, this resource group, anytime you want to create a resource with those properties. So we'll just do resource group spawn resources. We'll select the resource group triple. The new resource name is going to be magic, and its only volume with volume number 0 is going to have 100 megabytes of storage. So let's do that. And everything was successful. We should be able to find this resource definition now. Resource definition list. Here is our magic resource definition. automatically assign TCP IP port number 7001 for its replication link on DBD. And if we go to volume definition list, again magic, one volume with volume number 0, 100 megabytes as specified, and automatically assigned minor number 1001, which also means that it'll have DevDBD 1001 as the device. Let's do resource list, and we will find that it has been placed on 3 nodes again, Kronos, Remus and Romulus. And then let's do volume list, and here is, as predicted, DevDBD 1001, and it's thin provisioned, so it does not use a lot of storage. It has a virtual size of 100 megabytes, but currently it's actually only using 63 kilobytes because I didn't write anything interesting to it yet, not even a file system. So let's do that real quick. It's placed on Romulus, so I can just do that on the node that I have over here, mkfs txt4. Let's do that on DevDBD 1001, and my other volume is still mounted, so I'll unmount that, and then let's mount DevDBD 1001, and let's put a file here, touch mnt b4 snapshot, because I would like to show you the snapshot feature as well. Here it is, and unmount again. Now I can take a snapshot of this resource, and I'll just do snapshot create Kronos, Remus and Romulus, which is the 3 nodes where the resource was created. I could do it on a subset of those nodes, but I'd just like to have it on all of them. And the resource is magic, and this new snapshot name is going to be snap1. And here's our snapshot list. And now let's change what's on this resource so that we can see that the snapshot actually works. And I'll move the before snapshot file to be after snapshot now on the resource that I used to create the snapshot. And then there are 2 possibilities. I could either roll back the existing resource to whatever's in the snapshot, so roll back to an early point in time, or the other possibility is to create a new resource from the snapshot, and that's what I'm going to do now. So let's do resource definition, create snap view, so we can peek into the new snapshot, and this is going to be this resource definition where the snapshot is going to be restored. We will restore the volume definitions from the snapshot, from resource magic and from snapshot snap1 to resource snap view, and that will just restore the volume definition. You can see it here. It's now defined on the snap view resource definition, and then finally I can restore the snapshot itself into that resource. So snapshot resource restore from resource, that's again magic, from snapshot snap1 and to resource snap view, and that works pretty much like creating a new resource. So if I go into the volume list now, I can see that I have a new resource on the same 3 nodes where I had the snapshot. It has a new minor number. It also has a new replication link. If we take a look at the resource list, port number 7002 assigned. And if I mount this real quick, 1002, then here's your before snapshot file. And just to double check with the resource itself, here is the new file. So those two are now independent. They're different resources and they have different sets of data. And you could restore the snapshot again, so you can modify the restore of this snapshot. It's independent now, and then you can restore the snapshot in its original state again. You can do that as often as you want. Now let's clean this up again, and I'll show you how to add another volume to a resource. And that is not really hard. If you look at the volume list, we can see that FOSDEM21 has one resource. The resource has one volume. And if I want another one, I just go volume definition, create FOSDEM21, another one with 50 megabytes. That's the volume list. And now we have volume 0 and volume 1. And it has its own minor number, it has its own device, but it uses the same replication link. So resource list, still port number 7000. Both of those volumes in the same resource are using the same replication link. And it's still not usable. It says inconsistent when I'm still negotiating, because DBD does not yet know what to do with the new volume. It was not primary anywhere. So what I have to do next is just tell DBD where it needs to be primary, so that it can resync the volume with the other nodes. And I have set up a couple of DBD monitors here so that we can see what that looks like. So right now we have warnings that it is inconsistent. And I will select one of the nodes to be a primary. I'll do that directly here in DBD. Let's use the fourth one. Let's go to Romulus again. And all we need to do is dbd-adm primary --force FOSDEM21, and that will resync the volume, the new volume, and it will be available for use. And we can go back to secondary to go back to automatic primary secondary selection. That's it. And here we're back at the resource list, and now as you can see the volume is fully usable. Now let's do one more interesting thing, and that is to add a diskless client on the fourth node that does not have access to the data on the other three nodes. Let's do resource, create Kronos, FOSDEM21, and we're gonna say diskless, and that will automatically select the default diskless storage pool that you showed you in the beginning of this live demonstration. And if we take a look at the DBD monitors again, there you have it. And I should probably explain what you can see here. So this is obviously the resource name. These are the other nodes that it is connected to. Then the current resource role and the volumes. And you can see the difference here. Volume number 0, volume number 1, minor number 1000, minor number 1003. The ones that are marked in teal as the background color are the ones that actually have storage, and this one is marked in blue, which means it does not have a disk attached locally. It does not write to local storage. It's only using remote storage nodes for accessing their storage and making the volume available locally. And it's intentional. If it were unintentional, if it were diskless because the disk failed, then it would be marked in red, and it would give you a little bit more detail about what happened. So let's go to this node, SSH Kronos, and let's mount from there def drbd 1000 to MNT. And what you will see here is that we can access the same data without actually having the backend storage locally. So this is all just remote. It does not have an LVM volume here where DBD can write to. And we can look at that by just doing an LVS, logical volumes list. As you can see, no FOSDEM21 volumes. If we go back to Romulus, one of the storage nodes, and we do LVs here, then you can see those are the FOSDEM21 LVM storage volumes that DBD uses for actually storing the data. And it also shows that what LINSTOR does is pretty easy to find, because the LV just has the LINSTOR resource name and the LINSTOR resource number combined into a logical volume name. And most of the things in LINSTOR work like that, like DBD setup status. The DBD resource has the same name. You can find the DBD resource configuration file here, FOSDEM21. It's just a res file. And LINSTOR saves this, cat FOSDEM21. There you go. This is the DBD configuration file, automatically generated by LINSTOR, and it will be regenerated whenever you change something in LINSTOR, so you don't really have to care about it. But it's nice to have it because it even works if you shut down LINSTOR, and we'll try this out. One more thing that I would like to show you before I show you how DBD continues to work without LINSTOR actually running is what an auto tiebreaker is. So let's clean up here again. So if you create a resource that is only placed on 2 nodes, then what LINSTOR does is it'll automatically create a third resource on another node, and that one will be diskless, just so that you can use DBD's quorum feature. I'll call that tiebreaker, and the name does not matter obviously. And we'll do resource create only on Romulus and Remus with the tiebreaker resource. Storage pool is going to be the thin pool, and it'll give us a whole lot of information what it did. As you can see, tiebreaker resource tiebreaker created on default diskless store pool, and it actually placed on 3 nodes as opposed to only 2 nodes. So 2 of them are the ones that I selected, and the third one is Kronos, that was selected automatically with the tiebreaker feature. Now you can't really see this in the resource list. I can only see the 2 resources and the 2 volumes in the volume list that I created. But if you take a look at the DBD monitor, this is where you have the tiebreaker resources actually on 3 nodes, and one of them is a diskless client. Now, there is a possibility to show this in DBD as well, and you can just do resource list all and volume list all, and in that case it will also show you the hidden ones, the automatic tiebreakers that are normally not supposed to be used for anything other than quorum. And it'll say tiebreaker here in the state column, just to make it clear. Turning this feature off on a single resource is rather easy. You just delete the one that is the tiebreaker. So if I go resource delete Kronos tiebreaker, I delete it from that node. LINSTOR will automatically figure out that it should turn off the tiebreaker feature, and obviously also turn off quorum, because if you only have 2 nodes left, then quorum would not work. There's also a property in the controller settings where you can turn off the feature for all resources that are created on the controller, so it can be turned on and turned off globally depends on whether you want to use it or not. And then finally, let's stop LINSTOR, and I'll show you the LINSTOR processes again. Let's stop them. So this is the controller process, this is the satellite process. It can take a few seconds, but yeah, they're already gone. So if I try to reconnect here, I don't get any connection. It's not running on Romulus anymore. Also, the other satellites are not working anymore because the controller is gone. So what's interesting here is I think I do not have anything mounted, but I can mount again. And all those resources still work, even though LINSTOR is stopped. And that's what we call contour plane data plane separation, because you don't need the contour plane to have a working data plane. You can still do I/O on all those resources, and you can even stop and start those resources. DVD setup down all. Let's take a quick look at what the DVD monitor thinks. So it's completely stopped here. All the other nodes are complaining that they can't reach the DVD resource on this node. But I can just restart it because LINSTOR placed all the resource configuration files into a directory for me. So I can just do dvd-adm adjust all, and let's see what the DVD monitor thinks about that. And it starts up again. Let's go back. And again, all those resources still work. I can find my data on those resources. So what's nice about that is that you can do maintenance on LINSTOR, or you can upgrade LINSTOR, or you can even uninstall and reinstall LINSTOR, all while your applications are still running and your storage is still available. And that's the advantage of having a separated data plane and control plane. And I think that's it for this live demonstration, because we're running out of time. I hope it was interesting, and let's go back to the final slides. More information can be found on our homepage at linbit.com, and the projects on our GitHub page. Go to github.com/linbit and the various sub-projects from there. Thanks for watching, and have a great day.